When we're looking at a partial fractions problem and deciding how to break things apart, one of our rules is that when we have a repeated linear term like this, meaning the part in parentheses would just be the equation of a line, that I'm actually going to need to include both an x minus 2 to the power of 2 and an x minus 2 to the power of 1. So when I break this denominator apart, because I'm a little short on space, I'm going to get rid of the integration symbol. When I break that denominator apart, I'm going to end up with a 2x plus 1 term, an x minus 2 squared term, and then also a regular x minus 2 term. And please type in the chat if you're not able to see me, and I'll try switching. I've got 2 different Wi-Fi networks I can try switching between. Once we're here, the next step is going to be the same no matter which of the 2 methods you're using to solve for the constants a, b, and c. Either way, I'm going to start by multiplying both sides of the equation by that common denominator. So I'm multiplying both sides by the 2x plus 1 times x minus 2 squared. On the left-hand side, that's pretty straightforward. It's going to cancel out my denominator. But on the right-hand side, we want to be careful. We're distributing that whole piece into all 3 terms. So when I distribute this into the first term, the part that won't cancel out is x minus 2 squared. When I distribute to my next term, the part that won't cancel out is the 2x plus 1. But when I distribute to that last term, one of the x minus 2's will cancel out, and I'll be left with c times 2x plus 1 times x minus 2. Both the textbook and Dr. Didell mentioned that there are 2 different ways to solve for our constants a, b, and c. They will both work every single time, but in some problems, one method is faster than the other, and it depends on the problem which method will be faster. When I look at this, I see 2 nice numbers that we can plug in and make part of our equation go to 0. If I plug in 2, this piece would go to 0, and this term would also go to 0. And if I plug in x equals negative 1/2, this term would go to 0, and this term would go to 0. So I only have 2 nice numbers to plug in, even though I have 3 unknowns. So this could be a time where maybe you want to use the other method, but I'm generally speaking going to stick with plugging in numbers. So if I start by plugging in x equals 2, and remember I'm plugging that everywhere into this equation. So 2 squared, then I have 4 minus 10 plus 16. When I plug in the 2, this term goes to 0. When I plug in a 2 here, I'll have b times 5. And when I plug in the when I plug in 2 here, this last term will also go to 0. Oh, 4 plus 16, I'm at 20 minus 10, so that's 10 is equal to 5b, which means I've already found the value of b. It's going to be equal to 2. My next nice number to make some of the terms disappear would be to plug in x equals negative 1/2. Negative 1/2 squared means negative 1/2 times negative 1/2. It's going to be a positive 1/4. Minus a negative will make this plus 5/2 plus 16. When I plug in negative 1/2, unfortunately, this won't go to 0. Negative 1/2 minus 2. That whole thing would be squared. Oops, times a. This term will go to 0, and this term will go to 0. Now I have to actually deal with the fractions. So on the right-hand side, 2 is the same as 4/2. So negative 1/2 minus 4/2 would be negative 5/2 squared. Over here, 5/2 is the same as 10/4. So I'd have 1/4 plus 10/4, and I'd be at 11/4 plus 16. Now I've left things in fourths for now because I'm hoping nice things are going to happen. So if I take the negative 5 and I square that, I'll be at positive 25, and 2 squared would be 4. So now I've got 11/4 plus 16 is equal to 25a over 4. In general, I don't really like to mess with adding and subtracting fractions if I can help it. So I'm actually going to multiply this entire thing by 4 just to avoid the fractions. So I've got 11 plus 64 is equal to 25a. And 11 plus 64 sounds like 75. 75 divided by 25 means a would be 3. So we've already found the values of a and b, but we've run out of nice numbers to plug in. When you hit this point where you've run out of nice numbers, you can plug in absolutely anything you want. It's going to be a tight squeeze, but I'm going to try to fit it in over here. I'm going to go ahead and erase these zeros just to give a little bit more space. I don't know about you, but 0 sounds like a pretty nice number to plug in. If I plug in 0 for x, then on the left-hand side, 0 squared minus 5 times 0, I'm going to have 16. Zero minus 2 would be negative 2. Squaring that, I'm at 4, and we already know the value of a is 3. Two times 0 is 0, plus 1 is 1, and we know that the value of b is 2. When I plug in 0 here, 2 times 0 plus 1, I'm at 1, and then times the negative 2. So I'll have c times 1 times negative 2. Hopefully the numbers work out pretty well. So 16 is equal to 12 plus 2 minus 2c. And 12 plus 2, I'm at 14. And subtracting that over, I think I'm going to have 2 is equal to negative 2c, or c is equal to negative 1. We did all of that work, but we still have to integrate the function. Two of these are pretty straightforward to just write the answer to, the two that involve natural log. So this one, I know that I'm looking at 3 times natural log of absolute value of 2x plus 1, and then correcting for the chain rule on that 2, I'm going to divide by 2. This piece back here, again, this is another straightforward natural log. So I would be looking at minus ln x minus 2, and I'll squeeze in my plus c. This one right here, something different is happening. This is not a natural log. So we can take the time to write that out as a u substitution, looking at that x minus 2 squared on the bottom, I know that if I had 1 over x squared, that integral or antiderivative is not natural log. So coming off to the side here, 2 over x minus 2 squared, that's the same as having 2 times x minus 2 to the negative 2. And I think we can probably do this u substitution without actually writing it out. If x minus 2 were equal to u, then du would be dx. Integrating that, I'm going to add 1 to the exponent and get an exponent of negative 1, and then divide by that new exponent of negative 1. So I would have negative 2, x minus 2 to the negative 1, all over negative 1. Or, the nicer way to write that, the negatives will cancel. I don't really need to divide by 1, and x minus 2 to the negative 1 power means I can put it in the denominator.